Hello, here we have a force vibrations with viscous damping problem that we want to solve. So let us look at this statement and pick up some keywords here. So we have an unbalanced engine of mass 200 grams. Right, so this is mass. Unbalanced, which is, I'll put it as OOB, out of balance, mass. It is mounted on an undamped elastic support. What can we derive from this sentence? Right, undamped, meaning damping ratio zeta is equals to 0, and an increase in speed from 600 to 900 rpm will treble, right, the amplitude of the force vibration. We are asked to find the damping coefficient required for a damping device which will reduce the amplitude of vibration at 600 rpm by 10%. Right, so we have a case here that we want to design a damping device that we can reduce this amplitude by 10% when it's running at 600 rpm. So let us first start by writing down what we are given and what we are supposed to find. The out of balance mass, damping ratio 0. So rpm, to convert it to radians per second, will be 600. So omega 1 is for 600 rpm times 2 pi over 60, and we can convert it to radian per seconds. So likewise for omega 2 will be 900 right. So when we increase from omega 1 to omega 2, the amplitude trebles, right? So how do we represent that? So we have x2, which is the amplitude for omega 2, and we have x1. So if we increase omega 1 to omega 2, the amplitude of x2 will be 3 times of x1. So we have 3 over here, right? And we are asked to find the damping coefficient, which is C, when the amplitude of vibration at 600 rpm is reduced by 10%. So 600 is omega 1, the amplitude is x1, and if you want to reduce that by 10%, is 0.9 of x1 at 600 rpm. Right, so once we have this, it's easier for us to move forward. And now let us pull out the equation, right? For force vibration, the amplitude x will be equals to Fo over K divided by square root 1 minus beta square. Okay. So from this equation, first thing that we can substitute is the undamped situation where zeta is equals to 0, right? This is going to make this term to 0. So we have a force vibration problem where this force here, Fo, it is going to be equals to the out of balance force, OOB, out of balance force, which can be derived from M OOB E omega square, right? So OOB is out of balance. We have the mass here of the out of balance, which is in kilogram. E here is eccentricity, which is denoted by m, right? And of course omega is radians per second. So now we can substitute this out of balance force into our equation x, which will give us MOOB E omega square. So this whole term goes to 0, and now we have only this term here, right? So we have a square and the square root, and it will therefore be equals to k 1 minus beta square, and I've put a modulus in between this term instead of a bracket. So the resultant can, if it's a negative, it will become a positive. Okay, let's do some substitution and simplify this equation here. We notice we have a k here and an omega, right? And we know that k is equals to m omega n square, right? Notice this is a capital M, right, which is the mass of the entire system. MOOB is just the mass of the out of the balance for mass. Okay, so if k is equals to this, mathematically I can do this, multiply by k, the whole equation by k, and over m omega n square, right? Because this whole equation is going to be equals to 1. So I'm not changing the equation at all, and therefore here I can put E omega square. So I multiply my k here over k 1 minus beta square, and I have my m omega n square here. So now I can cancel off the k, and we notice this term here, the omega and over omega n is equals to beta, hence we can replace it with beta square, and this will give us equals to, here I've written down what we have just derived from the previous slide for the amplitude x. And next I would like to find the relationship of beta, the frequency ratio between 1 and 2, right? So we have omega 1, which is 600 RPM. We convert to radian per seconds. And we have also got omega 2 at 900 RPM, right? So beta 1 is omega 1 over omega, the natural frequency of the system, which is equals to 20 pi over omega n. And for beta 2, likewise is equals to omega 2 over omega n, and we get 30 pi over omega n. So beta 2 over beta 1 will be equals to 30 pi over omega n divided by 20 pi over omega n, and this is going to give us a relationship of 3 over 2. Okay, so we have the amplitude that travels when we increase from 600 to 900 RPM. Right, the amplitude travels, amplitude 1, right, when we increase from 600 to 900 RPM. So let's substitute our x2 with this equation over here. and we get let's do some cancellation of terms, right? So we can cancel this, we can cancel E, and I'm going to rewrite this equation on my next slide. Right, I've rewritten from where we left from our last slide here, and I've also substituted my beta 2 equals to 3 over 2 beta 1. Hence, my equation are all in terms of beta 1 over here. Right, the next few steps are all just more of algebra, so I'll go a little bit faster. Swoosh! That was really fast, but please feel free to press the pause button. Right, so now we have derived beta 1 as 0.4082. And let's move on to the next step when we add the damping. So now we are required to add a damping device to reduce the amplitude by 10% at 600 RPM. So again, let's substitute our x1 into this relationship. And we have derived zeta as 0.494, which is also equals to C over 2m omega n, right? So we are asked to find C, we have m, we need to derive for the natural frequency omega n. So beta 1 is equals to omega 1 over omega n. We have 0.494 is equals to omega 1 we have at 600 RPM, and therefore we can get our omega n as 153. Hence, zeta is equals to C over 2m omega n. I can put 0.494 is equals to C, which is the unknown we want to find, 2 times 200 kg, the out of balance mass, times my natural frequency 153.924. And we can solve for our damping coefficient, which is a C, is equals to 30415.4 Newton seconds per meter, which is going to give us, if we divide by 1000, 30.415 kilo Newton seconds meter. That's it. So we have the answer as 30.415, which is equals to the answer that we have here. Right, that's all folks. Thank you.